Now let's take some time and we look over proportions. Now a proportion is similar to a ratio in that a proportion is a set of equal ratios separated by a double colon. So earlier we talked about a ratio being expressed by a colon. A proportion is a double colon. Now proportions can be expressed as fractions as well as ratios. And a true proportion indicates that the ratios are equal. Just say for an example, if we say that 4 and 8 are a relationship and a ratio to each other, then we can say 6 to 12 would be another ratio, but we'd have to show the relationship of how those numbers are related to each other. So if we were to work this problem out and say 4 is to 8, just as 6 is to 12. We do a process of taking our inner numbers and multiplying them together, and then taking our outer numbers and multiplying them together. 4 times 12 would give us 48, and then 8 times 6 would give us 48. So we see here, this is a true proportion in that our inners are equal and our outers are equal. If you have a proportion where either a set of your inners and your outers don't equal each other, then it's not a true proportion. Now, proportion can be expressed one of two ways. It can be expressed linear or as a fraction. And we'll do examples of both of these because sometimes the way that people were instructed in math when they were in school, sometimes the instructor may have shown them one method. Other people may have been instructed a different method. There's no right way or wrong way to set up some types of problems because of the way that you are taught. As long as you understand the foundation of how you're trying to get to your goal, and if you work out the problems correctly and plug in your numbers into your formula correctly, then you'll get the right answer. Now, linear proportion goes left to right. So if we look at 2 is to 4, which is a ratio, and 6 to 12 is also a ratio. We can also read it as a fraction, as 2 over 4 is to 6 over 12. So if we go and take these problems and go ahead and work them out as a linear, 2 is to 4, just as 6 is to 12. Our rule is that we multiply our inners and we multiply our outers. 2 times 12 gives us 24, and then 4 times 6 gives us 24. So this would be a true proportion. If we were to set our problem up and work it as a fraction, 2/4 in relationship to 6/12, and what we do is we cross multiply. So in this case, 2 times 12 would give us 24, and then 4 times 6 would give us 24, and since our ratios equal out, then that determines that it is a true proportion. Always remember that if your ratios don't equal, then it's not a true proportion. Now you heard me mention earlier about the inners and the outers. Some people say innies, outies, however it was expressed to you and however you learned it. It's the same premise. We multiply the inner numbers times each other and the outer numbers times each other. And then from here, it will determine if they're equal, then it will show that we have a true proportion. So for example, if we said 4 is to 8, just as 6 is to 12, 4 and the 12 are our outers. So 4 times 12 is 48, and 8 times 6 are our inners, and 8 times 6 gives us 48. So 48 is in relationship to 48. So in this case, this would be a true proportion. Let's look at an example of inners and outers. If I have 3 is to 7, which is a ratio, in proportion to 9 to 21, which is another ratio. If we multiply our outers, which would be 21 and 3, would give us 63, and then multiply our inners, which is 7 times 9, would give us 63. If we look at the next example, 4 is to 9, just as 12 is to 27. We multiply our inners, and we multiply our outers. 27 times 4 gives us 108, and then 9 times 12 gives us 108. So this shows us that this is a true proportion. Now, we can also use the cross multiplying method, which is the fraction method. So if we had 4 eighths in relationship to 6 twelfths, 4 times 12 equals 48, and 6 times 8 equals 48. Another example, if we took 5 over 15 in proportion to 9 over 27. Now 9 times 15 gives us 135, and then 5 times 27 also gives us 135. Now keep in mind that we talked about earlier, when we're dealing with fractions, sometimes it's easier to reduce our number to come up with a smaller number so that we don't have a multiple that's so large, because larger multiples can tend to lead to errors. If we were to work this problem out, 5 is to 15 in relationship as to 9 to 27, we cross multiply. So 27 times 5 is 135. And then 15 times 9 also gives us 135. So this would be a true proportion. Another example of a true proportion would be 3 is to 9, just as 9 is to 27. We multiply our inners and we multiply our outers. 27 times 3 gives us 81, and then 9 times 9 also gives us 81. So this would be an example of a true proportion. Let's look at another example that deals with weight. If we have 2 milligrams, which is in relationships to 4 milligram, is direct proportion to 8 milligrams to 16. We follow our rule and take the inners times the inner and the outer times the outer. 16 times 2 gives us 32, and 4 times 8 gives us 32. So this would be an example of a true proportion. Now sometimes we have to solve for x, and x is a variable. Sometimes in a proportion or a ratio, you may have 3 out of your 4 that you're looking for, and your x may be located within your inners, or your x may be located within your outers. If you have 3 out of the 4, then you can always find your fourth. Just keep that in mind when you're solving, whether you're doing a concentration, whether you're doing a ratio, whether you're doing a proportion, whether you're doing a fraction. As long as you have 3 of your 4, then you can always solve for your unknown. Let's take a look at this example. Let's solve for our unknown variable, which is x. 4 is in relationship to our unknown, just as 3 is in relationship to our 12. The rule still goes the same. We multiply our inners and multiply our outers. So 3 times x equals 3x, and then 12 times 4 equals 48. We cancel out the one side of our equation to get our variable and to get our number on the other side. 3 divided by 3 will cancel out, which will leave our x, and then 48 divided by 3 would give us 16. Let's take a look at another example. If we're solving for our unknown, if I had 16 grams, which is in relationship to our unknown, is in proportion to 0.4 grams to 0.15 grams. Our rule stays the same as multiplying our inners and multiplying our outers. So 0.4 times x would give us 0.4x, and then we would take 16 grams and multiply it times 0.15, and then 0.16 times 0.15 would give us 0.024. We divide each side by 0.4 to get our variable on one side, and then 0.024 divided by 0.4 would give us a value of 0.06 for our x. Now let's look at another example. A man who is 5 feet tall stands next to a tree that is 12 feet tall. If the tree casts a shadow of 28 feet, what is the shadow of the man? Now this is an example of a ratio proportion. Now we can do this one of two ways. We can do this linear, or we can do this as a fraction. The key is when we are doing ratios and proportions, this is an example that I talked about. As long as you know 3 out of your 4 variables, then you can solve for your unknown. The key is is setting up your problem correctly and looking at what is in proportion to what. Now we can do this two ways. We can set this up as a proportion of the man's height as a relationship to the height of the trees, or we can set this up as the man's height to the height of the tree in relationship to the tree and the tree's shadow. So first thing we need to do is identify what we have. The man is 5 feet tall. The tree is 12 feet tall. The man has a shadow, which we don't know, and the tree casts a shadow of 28 feet. So if we did this linear, we could say A is to B, just as C is to D. Or we can do this as a fraction and set it up as A over B is in proportion to C over D. So if we go linear, we can say the man is 5 feet in relationship to 12 feet of the tree, which is in proportion to the shadow, which is unknown, times the shadow of the tree. We multiply inners times inners, outers times outers. 12x would give us 140, and then we divide both sides by 12, which would then say that the shadow of the man is 11.67 feet. Going back and looking at what we did, multiplying our inners, 12 times x gives us 12x, and 28 times 5 would give us 140. Now let's look at another example. A physician writes for 300 milligrams of a tablet to be taken once daily. If the pharmacy only stocks 100 milligrams of that tablet, then how many tablets will be needed? Now we can set this up as a ratio proportion linear, or we can set it up as a ratio proportion as a fraction. The key is identify what we have and what we don't have. So we say A is to B, just as C is to D. We know that 100 milligrams is in proportion to 1 tablet, so then 300 milligrams will be in proportion to our unknown amount of tablets. We multiply the inners and we multiply the outers, so 100 times x gives us 100x, and then 300 times the tablet gives us 3. So we divide both sides by 100. The 100 will cancel on the left, leaving the variable x, and then 300 divided by 100 would give us 3 tablets to dispense. Let's look at another example and solve for our unknown. You are the equipment manager for the baseball team. Normally, you make Gatorade for your team of 18 players using this recipe. You use 10 gallons of water, 7.5 scoops of powder, and this will fill 1 bucket of Gatorade. Today is your annual picnic, and you are expecting all 12 teams to be in attendance. So the coach instructs you to make enough for all of the teams that will be there. How many gallons of water will you need? How many scoops of powder will you need? And how many buckets will you fill? And this is another example of a ratio proportion. Remember we talked about earlier, as long as you know 3 out of the 4, then you can solve for your unknown. Now as we look at this problem, your recipe fills 1 bucket to treat 1 team of 18 players. So for your picnic today, you're making enough for 12 teams. So one of the things that you see is that your multiplication factor is going to be 12. So you have to think through, if my recipe makes enough for 1 team, then what am I going to need to make enough for 12 teams? So that means I'm going to need 12 buckets. And somewhere I have to figure out what is going to be the relationship of my scoops of powder and my gallons of water. Now, what we can do is we can solve for each ingredient. Now, if it takes 10 gallons of water to fill 1 bucket, 7.5 scoops of powder, we already determined earlier that there's going to be a multiplication factor of 12. So we're going to need 12 buckets filled total. So if there's 10 gallons of water, then 12 times 10 will give us 120, and then 12 times 7.5 would give us 90 scoops of powder. So if we set this up as a ratio, 10 gallons to 1 bucket as x, amount of gallons is to 12. We multiply inners times our inner and our outer times our outer. 1 times x gives us x, and 10 times 12 gives us 120. And that's how we derive at 120 gallons of water. If we look at our next ingredient, if it takes 7.5 scoops to make 1 bucket, then how many scoops will we need to make 12? We multiply our inners times our inners and our outers times our outers. 1 times x gives us x, and 7.5 times 12 gives us 90. So this would mean that we would need 90 scoops of Gatorade powder diluted with 120 gallons to fill the 12 buckets needed.